Welcome to Maths with EJD. In the last video, I talked about nonlinear systems and stability. Okay, so here I'm talking about Lyapunov functions and stability, to show another dimension apart from, linearization near equilibrium points. Okay, so Lyapunov functions, Lyapunov functions are a powerful tool for analyzing stability of dynamical systems, including chemical reactions, that is chemical reaction networks, and population models, just like the one we considered in the previous video, and population models. They help to determine whether a system will remain near equilibrium or deviate over time. In chemical kinetics, stability stability analysis is crucial for understanding chemical reactions, for understanding reaction dynamics, steady state behavior, and perturbation effects. This is when you change something a bit in the system, perturbation effects. So, similarly, in population dynamics, Lyapunov functions help assess species coexistence, extinction, and long-term ecological balance. Now, having said this, let's look at this next level where we look at Lyapunov functions and stability. Lyapunov functions and stability. So a function v of x is a Lyapunov function for a system x dot equals f of x, if number one, v of x is continuously differentiable, continuously differentiable, and positive definite, positive definite, and positive definite simply means that v of x is greater than 0 for x that is not equal to 0. And again, v of 0 is equal to 0, meaning that the function is always is greater than or equal to 0, as far as x is not 0. But when x is 0, the function is 0. When x is not 0, the function is greater than 0. Basically, that's what positive definiteness is about. Then number 2, its time derivative, its time derivative along trajectories, along trajectories, talking about v dot v dot of x is the same thing as the gradient of v multiplied by the function evaluated at f of x. So this now is is negative definite. It's negative definite. That's the derivative is negative definite, meaning that the derivative of v of x is always less than 0, and that indicating the system moves the system moves towards equilibrium. That's the slope, right? So it's like it's sloping downwards, so moving towards equilibrium. Okay, now if v dot of x is less than or equal to 0, so we say the equilibrium is Lyapunov stable. The equilibrium is Lyapunov stable, while v dot of x is less than 0 ensures asymptotic stability. Asymptotic stability. Okay, so let's look at applications in chemical reaction. Application in chemical reactions. Okay, so we want to look at the stability of a reversible reaction. So consider the reversible reaction. A goes to B and B returns to A. Okay. Uh, Perfectionism. Okay. A goes to B and B can go back to A. That's a reversible reaction. So in this situation, this reversible reaction is governed by uh, A dot equals A dot equals minus K1A plus K2B. And then B dot is K1A minus K2B, like that. All right. So we should understand that each of those terms, they have their meanings. Okay. So first of all, A and B, A, B are concentrations. They are concentrations of species, maybe chemical species, right? A and B. And then we also have K1 and K2. K1, K2 are forward and forward and reverse reaction rate constants. Forward and reverse reaction rate constants. All right. So with this in place now, okay, the rate at which A goes to B is K1, the rate at which B returns to A is K2. That's basically what this is about. Okay. Now, so how do we deal with this? That's the question at hand right now. So, so we can go like this. We want to find, we go for step one, right? Step one, we need the equilibrium point. Find equilibrium points. Find equilibrium points. And clearly we have the expressions. So of course we know that at equilibrium, A dot is equal to B dot is equal to 0. That's steady state. So it means that we have minus K1A plus K2B. So minus K1A plus K2B is equal to 0. That's called that equation 1. And secondly, you have K1A minus K2B also equals 0. Equals 0. Call that equation 2. So in that case, we also have to factor in the idea here that given that the initial concentration, A became B, right? But A had an initial concentration. Given that the initial concentration of A is A naught, we have from equation 1. So from equation 1, right, minus K1 plus K2B equals 0. That simply means that K2B equals K1A. K2B is K1A. That's when we transfer this. And that simply means that K1A is equal to K2B. Now, and for this to happen, right, B actually are derived from the difference between the initial concentration and the current concentration. So we then can have K1A equals K2 A naught minus A, initial concentration minus the concentration currently. So now we can look for A here. K1 equals K2 A naught minus K2A, all right? So we can collect like terms. So K1A plus K2A is equal to K2 A naught. Okay, so A is common into K1 plus K2, and that is equal to K2 A naught, all right? So that now A is equal to K2 all over K1 plus K2 A naught. So this is the current concentration with respect to the initial concentration of A, where the whole reaction started from, okay? So we can switch over to, so now we need B, right? So we can go to equation 2 for that. So from equation 2, okay, so from equation 2, we need to find B, right? So we have K1A minus K2B also equals 0. So now we have that K1A is equal to K2B. That means that K2B is equal to K1A, just like that. So B now is equal to K1 all over K2 times A. But now we have A is already given like this. Okay, so we have K2. So we have B now to be K1 all over K2 times K2 all over K1 plus K2 A naught. Okay, so that means K2 cancels K2. So B is equal to K1 all over K1 plus K2 A naught. So we have the equilibrium point. In fact, it's important for us to say this is A star now because these are steady state values, critical points. So these are critical points, right? These are critical points. Okay. This is B star. So we have those two critical points now. Maybe we can just make a statement here. So the critical points for the chemical reaction, that's the stable state for the chemical reaction, are A star, which is equal to K2 all over K1 plus K2 A naught, and B star is equal to K1 all over K1 plus K2 A naught. Okay, so we have this two like this. So the next thing we want to do is to define the Lyapunov, that's step one, right? Find the equilibrium point. So I found the equilibrium points now. So we need K2, all right? We need, I mean, step two rather, step two, where we define a Lyapunov function. Define a Lyapunov function. Okay, to define a Lyapunov function, we have this popular expression called energy, the Gibbs energy function or something like that. We can use that for the Lyapunov function, so we talk about a deviation from the critical point, and we now see how it comes back to the same point at the end of the day. Okay. Okay, I'm trying to locate that right now. Okay, so now for the Lyapunov function, right? Um, a natural choice, a natural choice is the Gibbs, it's called the Gibbs free energy function, the Gibbs free energy function, okay, which often serves as a Lyapunov function, as a Lyapunov function in thermo thermodynamic systems. Okay, so in that case now we have V of A comma B equals A minus A star. So that's the deviation from the critical points into B minus B star all squared. Okay, so from the very condition we have defined ahead, right, that for the Lyapunov function, V of x is continuously differentiable and positive definite. So that is if you put 0 for A and B now, so you get 0, but then if you put anything apart from 0, the answer will have to be greater than 0. And that works for this particular expression we have right here. So because if A is equal to 0 here, all right? So I mean if A is 0 here and B is also 0 here, so the worst you can have is actually 0. But then if A and B are different from 0, no matter what happens, because of the squares, right, you are guaranteed that the function will be greater than or equal to 0. So that's one very good idea for the Lyapunov function, in any situation. So in this case, that coincides with the Gibbs free energy in thermodynamical systems. Okay. So with that in place now, we have met the first condition for what uh, a Lyapunov function should be. So a natural choice is the deviation from equilibrium, which you have seen there, which the Gibbs energy actually gives us very clearly. Okay, so now let's look at when we differentiate that, what do we actually get? Okay, so that takes us to step three, where we differentiate. So step three is where we compute. I was going to write compute. That's compute V dot. That's V dot of X now. So we already have our V there. So from this V, we have V to be equal to A minus A star squared plus B minus B star squared, like this. So that means that V dot is going to be, differentiate this now, So we have 2 with respect to the A and B, right? Because this is V is a function of A and B. Okay, I can yeah, we already agreed up here that it's a function of A and B. So we are differentiating with respect to A and B respectively. So here we have, so if you differentiate this, bring down the power, differentiate A inside, that'll just be, it will take one outside, and then you now have you know um A minus A star, the power would be reduced by one, then you differentiate, you multiply by the derivative of A now. So with respect to A, okay? Same here. When you differentiate this also, you have 2b minus b star. So like implicit function. So you have b dot at the end of the day. But don't forget, we already have expressions for a dot and b dot. So now we can say now v dot would be 2 into a minus a star. What was a dot initially? A dot was a dot is the initial expression where we have minus k1a plus k2b. Okay. All right. So we have this now to be a dot is minus k1a plus k2b right here. And then we have plus 2 into b minus b star. And then b dot is k1a minus k2b. So if we have this now, okay, what this leads to is that we so this is v dot, right? A minus a star. So what actually happens here is that trying to see what that will give. Okay. So this ends up giving us what can we take out of this situation? Mm, 2 beta minus beta star k. Okay, and we already have the values of we have those values up there already. So, I mean, if you tidy up all this, let me just jump to the end. So if you tidy up all this, right, v dot is going to end up giving you minus 2k1 into a minus a star squared minus 2k2 into b minus b star squared. So if you put back all the minus the k1, the value of a and b that we had initially, so yeah, if you put back these values, all this k1 and k a star b star we got, if you put them there, right, and solve all of that, you're going to end up having minus 2k1 into a minus a star squared minus 2k2 b minus b star squared. So you can see this side is positive, this side is positive. So it is now guaranteed. The next condition is that this is clearly this v dot now. So we can say v dot is clearly less than zero. It's clearly less than zero. And once that happens, what do we have? V dot is clearly less than zero. And if v dot is clearly less than zero, what does the condition give us? It tells us that if v dot is clearly less than zero, so that ensures asymptotic stability. So we can conclude then, so we have v dot based on the fact that all this side is negative, this a positive positive because of the square. This place is guaranteed to be positive, and k1 and k2 are also positive. So minus and minus will guarantee that v dot is less than zero. So v dot is less than zero, and the equilibrium concentrations, okay, of A and B are asymptotically stable. They are asymptotically stable. Okay. So don't forget, I've jumped several steps from here to here. So you have to put back the A and the A star and the B star. I mean, the values of A and B rather, and then simplify. Okay. So A and B are asymptotically stable because it's strictly less than zero. Okay. Do an application. Let's do an application in, uh, let's do an application in population dynamics. Application in population dynamics. Okay. All right. So here we're looking at stability in the Lotka-Volterra predator-prey model. So we have that the Lotka-Volterra model, which describes which describes predator-prey interactions is given by this system. X dot equals x into a, or rather x into alpha minus beta y. Okay, x into alpha minus beta y. Then y dot is equal to y into delta x minus gamma, okay, where first of all x is the prey population, x is the prey population, okay, then y is the predator population, okay, then we have all the other things. Alpha is the prey birth rate, prey birth rate, okay. Then we also have beta. Beta is the predator birth rate. So the predator only gives birth, based on their interaction with the prey. So the predator birth rate, you can see it is in conjunction with the predator. If you expand this now, you're going to get alpha x minus beta xy. So that means that the predator only reproduces by deriving energy from the prey. Okay. So if you also expand this, you have delta xy. So now this is some kind of predation taking place. So predation, the predator population is increasing due to the predation on the prey, right? And then this is equal to gamma y. So gamma y now is the depletion of the population of the predator. That's death rate, like that. So delta is the predator, you know, delta is the predator reproduction rate, that's delta. And lastly, so you see this predator reproduction rate. Then lastly, gamma is the predator death rate. Okay. Now, with all of that in place, we can go ahead and first of all find the equilibrium point. That's step one again. Step one here, find equilibrium points. Find equilibrium points, like what we did, I think, in the previous video. Find equilibrium points. So again, don't forget the system. Find equilibrium points. So, setting x dot equals 0 and y dot equals 0, we find the following equilibrium points. We find the following equilibrium points. Okay. So for x dot equals 0, that means that x into alpha minus beta y is equal to 0. Okay. So that means we have x equals 0 or alpha minus beta y equals 0. So let's keep this. We did something close to this previously. So y dot equals 0 simply means that y into delta x minus gamma is equal to 0. So that means y is equal to 0 or delta x minus gamma is equal to 0. So that's another one. So we can classify now. We can group these things. So if we make a table like this and we say this is for the predator x and this is for the prey x and the predator y. So what do we have? We have x equals 0. So here x is 0. And then we also have alpha minus beta y equals 0. Okay. So that's for the x. And for y, we have y equals 0. And we have delta x minus gamma equals 0. Okay. So x is equal to 0. And here, yeah, we already know that that's x, right? So we have delta x minus gamma also equals 0. So it means we are going to have this possibility. We have 0, 0, we have delta x minus 0, 0, right, for both sides. X is 0, y is 0. Then x is 0, y is delta x minus gamma equals 0, right? I mean, because x is already 0, um, you know, since we have taken x to be 0, then this doesn't give us anything. So here we have alpha minus beta y, okay, comma 0 for y, and here we have alpha minus beta y, then comma delta x minus gamma. So we have these four possibilities, but the trouble here is since x is already 0 here, we don't get anything from here, and we don't, and then since y is 0 here, if we put the y to be 0 here, we don't get anything from here. So we have these two situations now. Okay, we have these two possibilities, all right, where which can be solved independently, right? So this is so if you look at this now, this can easily translate to alpha minus beta y equals 0, and then we have alpha equals beta y. So that tells us that y critical is alpha over beta. That goes. And then on the other hand, we can also have uh, delta x minus gamma equals 0. So that means that delta x equals gamma. So x is gamma all over delta. That's critical x. So delta over gamma. So those are the two things we have. So we find two equilibria, right? Um, so we find two equilibria. Find two equilibria. The first one is extinction equilibrium. We have extinction equilibrium where both the prey and predator die out. That's the extinction equilibrium, okay, where we have 0, 0. And then we also have the coexistence equilibrium, coexistence, coexistence, coexistence equilibrium, okay, where we have gamma over delta and then alpha over beta. So those are the two equilibria. So the next step is step two. Step two, okay. Uh, define Lyapunov function. Define a Lyapunov function. Don't forget the Lyapunov function must be positive definite, and then its derivative must be negative, strictly negative definite for us to say that there is asymptotic stability. But if it is less than or equal to 0, then we say it is Lyapunov stable. Okay, so let's see what happens in this case. So a function, a function often used, function often used for Lotka Volterra system or Lotka Volterra system is V, which is x comma y, and that is equal to x minus x star all squared plus y minus y star all squared. So what about the value of v or yi in this case? You can always guarantee that v of x comma y is always greater than or equal to 0. So it's always positive definite, you know. Then the worst case scenario is that if x and y are 0, so you see v 0, 0 is that's the only time you can have 0, and that meets the condition for Lyapunov exponent. Okay, so the next thing we want to see now is the derivative, right? So when you differentiate this, what do we get? So there we have step 3 where we compute. So we compute v dot. Okay, we want to compute v dot. So in this case now, we have that, of course, we already have our v of x comma y to be x minus x star all squared plus y minus y star all squared, which is positive definite. So if we differentiate, we have to do partial derivative for each one, right? V dot of x comma y now will give us like what we had before. So that's 2 into x minus x dot, x star multiplied by x dot to balance that up. Then y minus y star squared multiplied by y dot, okay? So, and you remember what y dot used to be. So we can bring those back. So v dot x comma y is 2 into x minus x star into x dot. Remember, x dot was x dot is x into alpha minus beta y, then plus y minus, yeah, 2, so this will also be, yeah, so the power should come down here, sorry. So this power 2 should come down here. We have 2 before that can work. So y into y star, multiplied by y dot, which was also y into delta x minus gamma. Okay, so we have this system now. This is one system, don't forget. So we have this now. Now, what happens now? We have computed, and if you look at the way this system is, of course, we need to bring back the. Okay, I guess since X and Y they are not as complicated as the previous one. Okay, so we may have to bring them back here. So if we bring them here, of course, first of all, if we put 0, everything just cancels out. So X 0 is not going to work in this situation. So we have V dot X comma Y. Okay, and then this is 2 into X minus X star. All right, and then um this is we have x minus x star, right? Okay, I mean, you can work that out. We already have our alpha, we already have our x star and y star. So to avoid wasting time, okay, so you can just use this, okay, 0, 0 is not working. So we use the second one, right? So just put this for x star and y star, you know, and then we can walk around all this. So let me leave that alone and just make the conclusions that follow from here. All right. So first of all, we see that v star of xy is not strictly negative. It's not strictly negative when we evaluate all that. It is not strictly negative. All right. So there are possibilities of negativity. So that means that v star of x comma y, it can be less than or equal to 0. So it's not strictly negative. So that meaning is the equilibrium is not asymptotically stable. It is not asymptotically stable, though it is Lyapunov stable. It is Lyapunov stable, it is Lyapunov stable. And that, of course, you remember we derived that from when we're talking about Lyapunov function initially. So the last line, if it is less than or equal to the equilibrium is Lyapunov stable, while this ensures asymptotic stability, which is stronger than Lyapunov stability. So this is just like halfway stable, so to speak, you know. So, with that said, now we can then talk about the next point that so this is first star, second star. Now, we have that instead the system exhibits periodic oscillations, periodic oscillations. So we have the idea of center or something like that, periodic oscillations, where populations 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 fluctuate in a cycle. So that brings up the idea of a limit cycle, like we saw when we're classifying equilibrium points, I think in the previous video. So this means the coexistence the coexistence equilibrium is neutrally stable. It is neutrally stable in the sense that small perturbations, small perturbations, small perturbations lead to sustained oscillations, leads to sustained oscillations rather than convergence equilibrium. What we had for the chemical reaction was convergence equilibrium, because it's clear that the V dot was less than or equal to, was less than zero, strictly less than zero. Okay, so what do we conclude here? Unlike the chemical reaction, unlike the chemical reaction case, unlike the chemical reaction case, right? The predator-prey system, the predator-prey system, okay, does not does not settle to a fixed equilibrium. Does not settle to a fixed equilibrium, okay, but oscillates, oscillates. It's like my handwriting is oscillating there, but oscillates indefinitely. So it just continues in that cycle, oscillates indefinitely. Okay. So we see that for chemical reaction, we have a steady state concentration, which is asymptotically stable. The system returns to equilibrium. For the population dynamics, we have predator-prey coexistence, which is neutrally stable because oscillations is always around equilibrium. So we see that chemical reactions tend toward fixed equilibrium due to thermodynamic constraints, while population dynamics often exhibit cycles, meaning coexistence does not always imply stability in the traditional sense. Okay. So that's what this has been like. Now let's see if we can get some practice questions to close it off. So let's see some practice. Practice. Okay. That's one now. The reversible, consider the reversible reaction where A goes to B and B can go back to A, right? And this is governed by A dot equals minus 2A plus 3B, then B dot equals 2A minus 3B. So for reversible reaction, the structure is always like this. So don't forget there's an A naught that helps your understanding. So the question is to propose a Lyapunov function, propose a Lyapunov function and determine if the and determine if the equilibrium determine if the equilibrium is asymptotically stable. Okay. Okay. Asymptotical stability is when V dot is strictly less than zero. Okay. But Lyapunov stability is when it is less than or equal to zero. Um, mm, okay, let me just give this as number 2. Consider the consider the Lotka Volterra model. Okay, where you have x dot equals x into 1 minus y, and you have y dot equals y into x minus 2. Okay, so the question is to determine the stability, of each equilibrium using a Lyapunov function, Okay, so let's make this like number 3. Number 3 now. Okay, I guess I'm gonna have to reconsider here. Yeah, let me introduce the concept. Since we've done population dynamics, let's bring the idea of a disease model, a model that talks about disease spread. Okay, let me bring that as number 3. I'll be talking about that deeper in the future. I don't know when, but I'll definitely talk about because that's my area of research. So consider an epidemic model. Consider an epidemic model, okay, where S dot, that is population of susceptibles, equals BSI, okay, and I dot, as those who are infected. This is an SI model where you have BSI minus gamma I, okay. Uh, so the question is to find, first of all, the disease-free equilibrium, the disease-free equilibrium. So that's the equilibrium where there's no disease, where I is equal to 0 and S has a value. That's the disease-free equilibrium. So the next question is to define, so you want to define a Lyapunov, function, and determine if the if the disease dies out, or persists. Okay. So it's still basically about, we'll be talking about asymptotic stability or Lyapunov stability. All right, so let me see your answer in the comment section, either on Facebook or on YouTube. And of course, let me also know in the comment section how helpful these videos are for you. And if you'd like me to solve a problem or answer a question, or teach a topic in particular, so I may be able to do that along the line. Then apart from that, you also want to subscribe if you haven't done that already. For this one, I've done it. Thank you. And for everyone, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And don't forget to like and share also so that more people can have access to this great content. So like, come your way again. Keep doing maths right. Bye.